At first, this USA-made filament appeared to be a typical PC-CF material. However, in the creep testing, it outperformed even the PPA-CF. Hello, welcome to my tech farm. I'm preparing a PC-CF comparison video, and at that time I had only 5 filaments, and I asked my pattern supporters if they want me to extend the list. And here you can see the final list. Many of them voted for exactly this filament. This is 3DXTech CarbonX PC+CF because it is made in the USA. This is not cheap filament, but the shipping from the USA to Europe is even expensive. But luckily, thanks to help of my pattern supporters, I found a reseller in the Europe. With this, the price of the filament was a little bit expensive, but the shipping was quite normal in this case. The price of this filament is $88 for 750 gram spool in the USA. And I just mentioned this because thanks to the polymaker and thanks to my pattern supporters, I don't care about these things, I just mention it, but basically I can buy any filament I want to test. Few specifications from the website. High thermal properties, near isotropic shrinking. This means the shrinking is very similar in X, Y and Z direction. Improved stiffness, dimensional stability thanks to the added carbon fibers. And this is typical that the fibers, glass or carbon fibers, will make the part stiffer, better dimensional accuracy, and with this easier printing compared to no fiber version. The printing temperature between 280 and 310 degrees Celsius. And the spool is already open because I already printed those test objects for that comparison video, but I also printed the objects for review of this video. They are a little bit different because I don't want to use the same test objects for 2 different videos. CarbonX PC+CF, made in the USA. This was just the welding line, the bag is not resealable. Well, for that review video I already measured how brittle is the filament. It's quite brittle, but let's see those footages. Start angle 22 degrees. Around 95. Moderately brittle. On sticker we can see the information about print and bed temperature, and I like this kind of open spools because the moisture will not stick inside during the drying. And I'm missing here the information what is the maximum temperature for the spool, for example, for drying. It will get a longer drying on 85 degrees Celsius in this case, inside the Sovol SH03 filament dryer. And as you can see, I'm not using these holes for locking end of the filament. They are quite good designed, but this is still very brittle filament, and just in case I'm using this clip which is printed from the ABS because it must withstand this high temperature drying. And now let's see the slicer settings. Generic PPA-CF is the salt profile, chamber temperature 65 degrees Celsius, on the bed 115, and 310 will be on the nozzle, and 8 will be the maximal flow. And the part cooling between 0 and 30%. And I increase the minimal layer printing time to 4 seconds. First attempt not really successful. Well, I will stop this printing because it needs some drying. H2 printers are more sensitive to this kind of moisture, and I have the feeling if I would print this on X1 carbon, it would be fine, but I don't have actively heated chamber, so I will dry the filament and reprint the test objects. And the drying 85 degrees Celsius, 6 hours. I saw this so many times with H2 printers. They are more sensitive to moisture. Looks like completely different filament. Last 2 vertical test objects, and it will be finished soon. Before the drying and after the drying. Definitely like completely different materials. And these are the test objects for that 8 PC+CF comparison video, because this one will be included too. Let's check the shrinking. It has some elephant foot, but I will measure above it. The design length is 80 mm and it looks accurate, but I still think that it has some shrinking, But from the side surface, I think it is not 100% dry filament and it has some overextrusion too. I cannot go into the details now, this was explained in my separate video. I need something for the practical example, but also for the thumbnail image. The dimensional accuracy is important here, but even then this was my second attempt. Tensile test with horizontally printed objects. Quite strong. For the comparison, I will use the average PEKK-CF or GF, and I have 11 in that pattern summary table. And this is quite strong filament. I mean, anything above 100 kg tensile strength is good, and it is very similar in this case to the average PEKK-CF. Layer adhesion, vertically printed specimens. Not bad. This is my table with the rating for this test object. And we can see that these filaments have a great layer adhesion, just a little bit weaker compared to the average PEKK-CF, but this is very good too. Shear test side by side, horizontal and vertical. With horizontal just a little bit over the max load. In horizontal position a little bit stronger compared to the average PEKK-CF, printed in vertical position a little bit weaker, but more or less they are very close to each other. Torsion test horizontal and vertical. 1.7. For horizontal, loaded 90 degree rotation. And the maximum load. 2.3. As always, very similar numbers, but different brake types. Printed in horizontal position, very similar loads at 90 degree rotation. Printed vertically, the PC-CF is stronger compared to the average PEKK-CF, but here I have a reduced number of the test objects because I started this type of the test much later. 3-point bending test. Distance between supports is 50 mm, and these loads are placed one by one, and I'm measuring the deformation after 1, 30 and 60 seconds. This is under 10 kg, almost no additional deformation. After the test, very minimal permanent deformation. Very similar behavior between these two filament types, just a little bit less initial deformation with the PEKK-CF, and only on 10 kg it became almost equal. Another 3-point bending test, speed up without 2 times. And it breaks suddenly. And here is the graph, max load bending strength and elastic modulus. Another test which I started much later, and I don't have enough data. I have only 4 pieces, fiber reinforced filaments, and not just PET, in that summary table when I am recording this video. And compared to that one, this PC-CF is stronger in both bending strength and elastic modulus, which depends from the deformation too. IZOD impact test. Charpy impact test. And side-by-side results from 3 measurings. On Charpy test I don't have enough data, only one, that's the Polymaker PEKK-GF, so it is not presented on the graph. On the IZOD I have enough data even for the average PEKK-CF, and we can see that this PC-CF is tougher compared to the average PEKK-CF material, and it is more brittle compared to, let's say, ABS, but at least 2 times tougher compared to the average PETG. Creep test the deformation on the constant load of 1.25 kg. Very minimal deformation. 13.20. The deformation is so small that I have to go around. It cannot go through this gap. Day 5, the last measuring, and almost no deformation so far. 13.21. This small deviation is just result of inaccuracy in the measuring, but basically absolutely no creeping of this material. So we can see significantly less deformation on this PC-CF compared to average PEKK-CF. Now PPA would be somewhere here below 13, but the creeping is the difference between 2 days, which is presented on the second graph, and basically creeping of this PC-CF is 0. This is just an inaccuracy in the measuring, and even with the PPA I could measure some creeping of 0.2 mm or something like that. So in this case the creeping is better with this PC-CF filament. Temperature test in the oven. When I want to record the temperature of the first deformation, M10 nut is a small load, And this PPA-CF started with deformation at 164 degrees Celsius, which is above typical for this type of the filament. The experiment I stopped at 180 degrees Celsius, and of course the object is flexible now. I already mentioned that this is above the typical for the PPA-CF filament, but compared to the average PEKK-CF, this is lower, but this can be significantly improved with the annealing. All results one more time: creep test, tensile test, layer adhesion, shear test, bending test, the deformation after 30 seconds, bending test, the deformation under these loads after 1, 30 and 60 seconds, torsion test, horizontal and vertical, impact test, IZOD and Charpy, temperature test, and that second bending test. I already mentioned that I'm preparing that 8 PPA-CF comparison video, and in most cases there will be some kind of blends, usually PC-PBT blend. Here I couldn't find any information about the blend, and having this high temperature resistance, I believe that this is very close to the pure polycarbonate reinforced with carbon fibers. But this means also that it is a little bit harder for printing, and I noticed that this 65 degrees Celsius chamber temperature is really on the edge, so this filament could really benefit from even higher chamber temperature. Compared to other PPA-CF filaments, which are PBT blends for example, they are much easier for printing and they can be printed even with a lower chamber temperature. So this was my experience with this 3DXTech PPA-CF filament. If you have some other, fill us down in the comment section. Huge thanks to the Polymaker for sponsoring my channel and to all my Patreon supporters, and together they make this kind of videos possible. And to all the others, I thank you for watching this video till the end, and happy printing!